The other one, that the last thing that I want us to quickly discuss today, if you check section H of that chapter in our textbook, you will see the parallel box and whisker diagram, or simply the parallel box plot. Okay? And there's nothing strange about it. It's just a way of comparing two distributions. So the one we have just talked about is for a single data set, like on one variable, if I may put it that way. For example, we are talking about, we classify maybe the data set into maybe by gender, for example, and the first data set is about the men, the second data set is about the women. Then we can have two set of box plots, and of course they will be parallel, apparently. So that's just the difference. Okay, there's no, every other thing remains the same, just as we have discussed. So if you want to visualize two set of data sets, you will have that. So let's listen to this. Then the feedback we talked about earlier, I will also put that in the video, especially because of Krista. So I will explain what Mr. Cheng has been able to help us with earlier. Oops.
We often want to compare two different data sets.
Okay, start again.
In statistics, we often want to compare two different data sets. In this example, we will use a parallel box and whisker plot to make a visual comparison of the distributions of the data sets. The data we compare is the time taken for two anesthetics to take effect. To draw a parallel box plot, we find the 5-number summary for both data sets.
Separately.
For the old drug, you should find that the minimum value is 5. The lower quartile is 8. The median is 10. The upper quartile is 12.5. And the maximum value is 21. We draw a box plot for these values, labeling the number line as time in seconds. The number line must cover the ranges of both data sets. For the new drug, you should find that the minimum value is 7. The lower quartile is 8. The median is 9. The upper quartile is 10. And the maximum value is 12. We draw a box plot for this data above the other data set on the same number line. We can now compare the two sets of data visually. The hospital wishes to know which drug acts faster, so we will compare the medians of the data sets. The median for the new drug is 9 seconds, compared with the median for the old drug, which is 10 seconds. So, the new drug is generally a little quicker in taking effect. The hospital also wishes to know which drug is more predictable, so we will compare the spread of the data sets. The range for the old drug is 16 seconds, compared with the range for the new drug, which is 5 seconds. Also, the interquartile range for the old drug is 4.5 seconds, compared with the interquartile range for the new drug, which is 2 seconds. Using either measure of spread, we conclude that the new drug is more predictable than the old one.
Okay, so the whole idea is, if you have two set of data, of course related, in this case they're talking about medications, maybe some improved version. It could be the case of, so if I want to make it like a personal scenario like we are dealing with right now, it could be the improved version of the COVID vaccine based on the newly discovered strain, either the Brazilian one, the UK one, or the South African one, something like that, and can come up with, oh, which of these works faster, what do you notice about this new whatever. So when it comes to comparison, you can have that. Can I ask a question? What if we are talking about 3 sets of data? Do you think the box plot will be a good way to compare the visualization? Can we have 3? Do you think we can have 3? Yeah. Of course, there's no restriction. It's just a parallel, right? It doesn't mean you can't have another one. Okay? It could be, oh, the vaccine 1, vaccine 2, vaccine 3, something like that, and from there. So again, one of the instructions is you have to consider the range of the 2 data sets. So which means before you can draw your box plot, you need to consider what is the minimum, what is the maximum for each of them, so to know the range. And of course, you do not have to begin with 0. I think we clarified that during your practice. You don't have to begin with 0. If 0 is not part of the data, all you have to do is use this, which shows that it still continues. But I want to believe the reason they mention 0 is because of the time. Remember, you can't say negative time, right? So again, if you don't want to use the arrow, because arrow shows it goes indefinitely. Of course, it doesn't go indefinitely in the case of 0. You can just start with 5 and don't put anything, if 5 is the least in this case. And if 5 is not so far from 0, why not just show it? But if you're dealing with 33, of course, you don't want to draw up to 0. Like, it's just a waste of time. As you can see from some of the IB past question, like 0 was never included because it wasn't necessary. Okay, then the last but not the least, we're going to leave in about 1 or 2 minutes. So we were wondering about this quartile thing. So let's finalize again, especially for the sake of Krista, who is home. So the first thing you should do, henceforth, forget about the n+1, whatever that we discussed. Of course, do your n+1, 2n + 1 over 4 here, which is n+1 divided by 2. Do this. So again, the whole idea is midpoint. The midpoint between data 1, 2, 3, up to data n is simply the addition of the n divided by 2. So yes, this makes sense. Okay. Now, if you do this and you find yourself in position x, definitely what you are looking for is between position 1, this divide distribution into 2, yes? So before the distribution, you have x minus 1 position. And after the distribution, you have the x plus 1 position. So which means your Q1 is exactly halfway between these two. Okay? And exactly halfway between these two will be this plus this divided by 2, and that will just be x over 2. And exactly halfway between this and n, because the Q2 divides into half. So there's another set of exact half here, while your Q3 is exactly halfway of that as well. So again, using midpoint, either midpoint in statistics or in coordinate geometry, we've talked about that. Remember, even in coordinate geometry, midpoint is x1 plus x2 divided by 2, y1 plus y2 divided by 2. In estimated mean, our midpoint is always extreme end of this boundary, something like that, divided by 2. So the same way, if you have these 2 and you divide by 2, you're going to have x1 plus n divided by 2, and that tells you the position of Q3. So I think that is an easier way to do it. So I think we went in one specific case. Let's say you have a data set that is 100 in number. 100 in number. So you have position 1, 2, 3, up to position 100 in the frequency distribution table, right? So again, let's identify the median. The median is simply going to be in position 101 divided by 2, which is 50.5. So this is the position of the median, which means the lower part of the distribution is from position 1 to position 50, and the upper part of distribution will be from where to where?
51.
51 to 100. So again, your Q1 is half of this, your Q3 is half of that. Okay? So half of this will just be this plus this divided by 2. Half of this will be this plus this divided by 2. So the position of this will be 51 divided by 2, which is 25.5, yes? And the position of this will be what? 75.5. So once you are able to identify this position, it is easy to trace it in the cumulative frequency table or otherwise. Okay? Any questions? So I'm going to hand over the parallel box and whisker diagram worksheet by the end of today. Please make sure you are able to complete that before you come tomorrow. By tomorrow, we'll do the last part. Cumulative frequency curve, variance and standard deviation. And with that, we've completed this section. Thank you very much.